Welcome to the video tutorial on optimizing transcranial electrical stimulation using software tools. TES is a non-invasive brain stimulation technique that modulates neuronal activity by delivering low-intensity electrical currents through electrodes placed on the scalp. Optimizing the parameters of these electrodes is crucial for maximizing the effectiveness and safety of the treatment. In this tutorial, our goal is to introduce you to the concept of electrode optimization. In particular, we will cover direct current stimulation and guide you through the process of using software tools to achieve optimal current patterns. We will be focusing on a specific software package, the Zeffiro Interface, which offers powerful features for modeling and optimizing electrode configurations. By the end of this tutorial, you will have a better understanding of the importance of electrode placement optimization, the key concepts and terminology related to TES, and how to use software tools to optimize electrode placements for specific target areas in the brain. Whether you are a medical student, researcher, or a professional in the field of neurostimulation, this tutorial aims to provide you with valuable insights and practical guidance on optimizing electrode placements. As a first step, let's explore the benefits of electrode optimization and its significance in TES. Using a high-resolution 3D model of the patient's brain and optimizing the placement of electrodes and intensity leads to more effective stimulation, improving treatment outcomes for patients with various neurological disorders. Delivering the stimulation only to the target region minimizes the risk of unintended stimulation of other brain regions. Optimizing algorithms allow for the creation of customizable treatment plans based on the patient's diagnosis and symptoms. This means that the stimulation can be tailored to the specific needs of each patient. As was already said, TES is a non-invasive procedure that does not require surgery or anesthesia, making it generally safe and well-tolerated treatment option for patients. Now that we have a brief introduction, let's dive deeper into the terminology and related concepts. Focused current refers to the electrical current that is specifically targeted towards a particular region of the brain. Nuisance current is the electrical current that is not focused on the desired target region and may stimulate other unintended regions of the brain. The optimization process aims to maximize focused current in the target region while minimizing nuisance current in non-target regions, ensuring effective stimulation and minimizing side effects. Intensity refers to the strength of the electrical current delivered to the brain during TES. The intensity of stimulation can be adjusted based on the specific treatment goals and individual patient factors. Focality refers to the degree of precision with which the electrical current is targeted towards a specific region of the brain. Higher focality means that the stimulation is more precisely targeted, resulting in better treatment outcomes and reduced side effects. Intensity and focality are closely related in the sense that they represent two key factors that need to be balanced during TES optimization. The intensity-focality trade-off is a balance between strength of the stimulation, the intensity, and precision of targeting, the focality. This trade-off is critical for achieving effective treatments while minimizing side effects. Reconstruction is the process of creating a 3D model of the brain from raw data, such as images from MRI or CT. The primary goal of reconstruction is to generate a detailed and accurate representation of the brain's structure. This reconstructed model can then be used for further analysis and simulations. Finite element simulation is a numerical method used to solve complex problems in engineering, physics, and other disciplines. It involves breaking down a large problem into smaller, simpler pieces called finite elements. So a complex system, such as the human head and brain, is represented by a mesh of these finite elements. The simulation uses properties of these elements and their interconnections to model the behavior of the system under various conditions. For transcranial electrical stimulation, finite element simulations are used to model the distribution of electric fields within the brain based on electrode placement, tissue properties, and other factors. Lead field matrix is a mathematical representation of the relationship between the electrical currents delivered by electrodes and the resulting electric field in the brain. This matrix is used in the optimization process to determine the best electrode configuration that achieves the desired stimulation effects. Later, we will discuss how to perform a parcellation, convert it into finite element matrix, and compute the lead field. This series of tutorials is based on a key paper about comparing L1 and L2 norm regularized and least squares fitting methods in optimizing the electrode placement for focal multi-channel transcranial electrical stimulation. The paper presents the following parameters. Alpha is a parameter that controls the strength of penalizing non-zero currents in the optimization process. It determines the balance between the intensity and focality of the electric field by adjusting the amount of penalty applied to non-zero currents. A higher alpha value encourages a sparser distribution of currents, resulting in a more focal stimulation, while a lower value allows for more widespread currents, leading to a less focal stimulation. By adjusting alpha, the optimization algorithm can find the best intensity and focality trade-off while achieving the desired therapeutic effect. Epsilon is a parameter that controls the threshold for the nuisance field importance in the optimization process. A higher epsilon value means that the optimization algorithm will put more emphasis on minimizing the nuisance field, thereby reducing the risk of stimulating non-target areas. Conversely, a lower value means that the algorithm will focus less on the nuisance field, potentially allowing for a stronger stimulation of the target area, but with an increased risk of unwanted stimulation. These two parameters are essential to understand as they are estimated by the optimization algorithm and play a significant role in the process. The paper we've mentioned not only elaborates on these parameters, but also builds the foundation of the optimization algorithms around them, so we advise you to read it by following the link in the video description. In the next videos, we will delve into the Zeffiro interface, guiding you through the setup process of preparing patient data for computation, defining stimulation parameters, executing the optimization algorithm, and reading the results. See you there!